Right. So, yes, Ørsted fund the work that a lot of the work that I'm going to talk about, and fund the chair. They were Dong Energy, which stood for Danish Oil and Natural Gas. And they made a strategic decision to move away from oil and natural gas into renewables, and hence have changed the name. So you may have seen over the years lots of wind farms being developed by Dong Energy. That's now Ørsted, and they are one of the leading wind farm developers in the UK and indeed worldwide. So the talk I'm going to give is about the geotechnical design behind offshore wind, and I'm sure all of you have seen Magdalen Tower. And here is a model of Magdalen Tower, a replica of Magdalen Tower. It's about 40 metres high, or thereabout. I think it's 42. And I think the Tom building is about 42 metres as well, although I haven't been able to work it out. Maybe someone here will know. This is, to scale, a current offshore wind turbine, broadly speaking. So these are pretty massive structures, and you can imagine you have the wind hitting the structure, obviously turning the blades, generating electricity. This may be 3-5 megawatt turbine, and you have waves hitting it. I'm going to talk a bit more about all that. And the basic problem is, how do you anchor this structure to the ground to stop it falling over? What do you have to do? And different to oil and gas problems where you have very big, heavy structures, there's no weight to this structure, so it's very light. So the key problem is, how are you anchoring it to the ground? That's what I'm going to talk about. And indeed, there are many different concepts that people can consider. So that's current. If I just do a little trick, that is future. that is where it's going. So this might be 15 megawatts. It's an absolutely massive structure. Now, when you fly across over the water, maybe from Denmark to the UK, and you look out, you can sometimes see these wind farms. And bearing in mind how high up you are, you can still make out the individual turbines. That's how big they are. They're massive structures. So what I'm going to talk about is how we go about it, and some of the problems that we're encountering, and what Oxford Engineering is contributing to this activity, because we're right at the centre of trying to make these designs more efficient and more economical. Now, maybe I'll put this down on the ground so I'm not looking over it. But that will just remind you. Now, as Lionel mentioned during the AGM, the department, and during his talk, the department has been expanding, and in civil engineering we've been expanding quite a lot, and a lot of that focus has been in renewable energy, particularly offshore renewable energy. Now, I'm only going to talk about the geotechnical areas, and in this space we now have 7 staff, or in fact we will have 7 staff in January when our new departmental lecturer arrives. We have a doctoral training centre, which I'll talk about very briefly. We have a lot of industry collaboration. We work with most of the major wind farm developers in the UK, and including Ørsted, who are a major funder of the work. And we have lots of strengths in different areas of engineering, particularly theoretic modelling, analysis, lab testing, and field testing. And what I'm going to focus on in some of the lecture is field testing. And the thing is that these are very big structures. Even when you do experiments in the field, they're still small-scale experiments or medium-scale experiments. And I'll show you some of the ones that we've been doing. I'm not going to talk about fluid mechanics, but that's an area in the group, in the civil engineering group, that has really expanded over the last 10 years. And we now have 5 members of staff working in that area. And we have a number of people funded from external funds, particularly the Royal Academy of Engineering. We have 2 research fellows, as well as myself. And we also have an EPSRC research fellow as well. Now, we have what is called a doctoral training centre. And I guess I'm showing this because what we're very keen to do is create the next generation of technical specialists. This is through our graduate students. And so we run what is called a doctoral training centre in renewable energy marine structures. And this is to create the next generation of technical experts that can work in the sector and guide the sorts of developments that we need to take forward over the next 10 to 20 years. It's a collaboration with other universities in the UK. We're about a third of the activity focused on the geotechnical engineering. It's a taught program, but there is a taught element, but it's mostly research activities. And we have a lot of industry engagement with many people in the offshore wind sector, particularly consultants and also the wind farm developers. We run what is called a DEng, which is different to a DPhil. We have some DPhil students, but we have a DEng program, which is the engineering doctorate, which is more focused on industry run research. So that's a sort of a dual offering that we run. And companies like Fugro and Atkins are sponsoring some of our DEng students. Sorry. So, engineering of wind turbines. Here is a wind turbine. It is actually a very multidisciplinary problem and perfect for a department like Oxford, where we focus on engineering science. There's every element of engineering science in this problem. We've got design of these blades, you've got composites, you've got the fact that the blades have to pitch, you've got complex control algorithms, you've got the generator, you've got a gearbox, you've got actually to fabricate the whole structure, you've got mass production, you've got dynamics. I mean, these are very slender structures. You can imagine this thing vibrating quite a lot, particularly as the blades are rotating. You've got forces from the waves and the currents. These can be very considerable, particularly in deeper water. You've got to get the electricity to shore. And what I'm most interested in is how do you anchor it to the ground? But of course you can't see that in this picture. It's below the sea surface. But this sort of problem is perfect for the undergraduate course. And indeed, for 15 years, we ran a third-year project on the design of offshore wind, starting from shallow water and then more recently to deep water. And so a number of students on the course have been exposed to this problem and exposed to the sorts of work that I'm going to describe, which we've introduced into the project so that they're really focused on where the industry is at. We get them to focus on real sites and we give them real information so that they produce designs that are approximating the sorts of designs that the sector are building. And a number of these students have since gone on to do PhDs and also work in the sector. So this has been a very good flow of research back into the undergraduate course. Now some statistics, just so that we can be aware of the situation. And I'm not going to talk about climate change or why we should go for wind or not wind and nuclear, blah, blah. I'm not going to talk about that. That's not. I'm also not going to talk about the different types of wind turbines you could design. That's also not my concern. What I'm concerned about is the sort of pipeline of work that's coming through and how we're going to solve the engineering challenge of constructing these structures cheaply enough so that our energy prices don't go up too much. So I've got some statistics here just to show you the penetration of wind into the UK. And I think if you go onto, there's a national grid dashboard, it shows that the demand daily is about 40 gigawatts to give you a sort of order of magnitude of what we're drawing in terms of electricity. In 2017, wind contributed 15% of the UK supply. So this is quite substantial. I've got here some load factors. This is, if you like, the proportion of electricity generated from the wind turbine compared to its rated capacity. What I'm drawing from this is that onshore wind farms tend not to be as efficient as offshore wind farms. That onshore, the load factor is about 27%. Offshore, it's about 38%. And new build offshore wind, they're aiming for about 45%. So it's quite an efficient process. And the other thing that's of interest, in these brackets that you can see, this is the average, if you like, turbine size. So you can see that for onshore wind, the average turbine size is quite small, or relatively speaking, it's not small, they're big, but relatively. And for offshore wind, these are quite big, and the plan is even bigger. So an 8.5, 10 megawatt machine, it's not quite as big as this compared to this, but it's bigger than this compared to this. So it's in between. And there's a great website, Renewable UK, has great information on all this, worth looking at. This is the rate of construction. And I've got on the vertical axis installed capacity date. This is offshore construction, I should say. And this started from about 2000, where 2 turbines were installed off the coast of Blyth. They're sort of trial turbines just to see how it could be done. So back around here, and you can see a gradual ramping up. We are here, so we're about here. The dashed line is what's in construction right now and when they're planned to come on stream. And then the green arrows are my sort of estimates of where the consented wind farms, when they might be built. So it might be as early as 2025 or 2030. But these are wind farms that already have consent, so they are in design at the moment. Engineering firms are currently designing them. And what I'm going to talk about, some of the work we've been doing, is feeding into that design process right now. So it's quite a pipeline, and this doesn't actually show, if you like, the phase of work that might happen after that. What it also doesn't show is some of these turbines, by about here, this date, we'll need to start replacing some of these turbines. There's a renewal program that will have to come in stream. So there's a lot of activity, a lot of work that can be done. So where are they being built? Well, there was a lot of work done in the early days to look at the UK bathymetry. So this is on the left. The lighter blue is shallower water. There's a nice patch of shallow water here, but it's a fair way from the shore. Obviously shallow water here, some shallow water there. So there's a lot of work done to identify key sites that could be developed. They obviously correlated all that with potential wind speeds to make sure that when you develop these wind farms, you're making optimal use of the resource. So when they developed them out, or started planning to develop them out, they released the sites in phases. It was the Crown Estate released these sites. And in about 2001, they released the Round 1 sites. Now these were very much demonstrator sites, close to shore, and fairly small wind farms, say 30 turbines of about 2 megawatts each. So it's really just to prove the idea, prove the concept. Most of those sites are now built out and have been operating for some time. North Hoyle, I think, was the first wind farm site operating in 2003, 32 megawatt turbines. The Round 2 sites, bigger sites, a bit further from shore, 2003. And then the Round 3 sites, these are major sites. These are the ones in pink, 2010. These are effectively big offshore wind farm power stations. We're talking, the Hornsey site is a 6 gigawatt site. Hornsey 1 is over 1 gigawatt. Hornsey 2 will be 1.8 gigawatts. And then Hornsey 4 will be another 3 gigawatts. Hornsey 1 is being constructed. Hornsey 2 is in design. So, these are massive power stations situated offshore. And of course, across Europe, this is the picture. There's a lot of activity. And it's not only UK, Europe, it's also China. The US is now getting into it. Taiwan. Many places are looking at offshore wind. So, where we're talking, maybe 2,000, 3,000, 4,000 turbines, you multiply that by Germany, France, US, we're talking tens of thousands of turbines across the world. So I'm going to focus on the structural side of things really, or more importantly, the geotechnics, the foundation design. How do you design these structures to interact with the ground and still stay upright? There are many concepts, and all of these concepts we have done some work on in the group in Oxford. Just starting here, this is simply a gravity-based structure. If you have a big enough weight, then it won't fall over. There's sufficient downward force holding it in place. A monopile. This is simply a steel tube hammered into the ground. Majority of wind turbines sit on a monopile. This is a suction installed foundation. I'll talk a little bit more about this. This is a sort of novel type of foundation. Not used much yet, but much promise. In fact, I did my PhD on this in 1996 to 99. Was promising then, it's still promising. Now this one actually is more promising. This is a suction installed foundation with what's called a jacket structure. So where you have an offshore structure that's a space frame, that's a jacket structure. You could have a tripod type structure, and then of course we have the floating structures. There is a floating wind farm off Scotland run by Statoil, finished last year or early this year, called High Wind, 5 turbines. And so floating is very much in play, but clearly for deeper water. Now we're focused on the shallower end of things, really up to about here, maybe 40, 50 metres of water. So the different structures, there are different problems. If you just have a single foundation or a single base, then clearly that base must resist the overturning moment that's applied. So somehow you must stop it from turning over. If you have a multi-footing structure, then the overturning moment, so that the force from the wind, will be translated into some vertical loads on the foundations. Now, if the load, the overall weight is quite heavy, then these reactions are in compression. But as the weight comes down, and if you wanted to cut costs, you cut weight, then you might get tension on this foundation. And that's a really tricky design problem, designing a foundation for tension. Now, I'm not going to cover that really in this talk. Most of the talk is going to be focused on this sort of problem, where we're trying to resist the overturning moment by something that extends into the ground. So this is just a schematic of what I described earlier, the turbine and the different sizes. And it could be Magdalen Tower, could be the Tom building. They're about the same heights. So 15 megawatts may be the future. That's what we're aiming at, maybe 20 megawatts. 100 metre long blades. It's huge. The largest blade currently made is 88.4 metres long for a production turbine, or is experimental turbine. Yeah, these are big. So that's where we're trying to get to. You can imagine the forces we're talking about. So here are the forces. So historic oil and gas structure. Very heavy, big horizontal forces, but actually horizontal force as a proportion of the vertical of the weight is small. 1 meganewton, 100 tonnes for the conversion. But you can see the horizontal force is about 1/8 of the vertical or the weight. For the wind turbine problem, the horizontal forces, so you've got the waves and the wind, they're actually of comparable magnitude to the weight. So this makes the design problem quite hard because you don't have weight on your side. And you don't want to add weight because that's going to cost money. And of course, these are sort of static forces. You can imagine the waves being quite cyclical, going up and down, up and down, up and down. Also, the turbine rotates. Maybe one rotation every 3 seconds. Okay? So there is an excitation on the system. So we need to be careful not to excite the natural frequency of the structure. As the blade passes the tower, that creates some sort of force on the system. So there's also the blade passing problem. So you have these excitations on the system that you need to avoid when you design the structure. In fact, it turns out that one of the critical things for designing a wind turbine is designing for its natural frequency and making sure that that is accurately predicted and avoids things like the blade rotation frequency or the blade passing frequency or the wave frequency or the wind frequency. So it turns out to be a difficult problem. Also turns out to be quite hard to predict. Now, I just show this because just to give you an idea of the sorts of waves that we're talking about. This is, of course, deeper water than most wind farms might be in. This is the surface elevation of a wave stream that passed through a structure that was fully instrumented. So this is a novel structure that Statoil put up in the North Sea. Because it was quite novel, they had instrumentation on it. Turns out, as soon as they put it in, it more or less received its 1 in 100 year design storm. It's probably the only time ever that an instrumented structure has received its design storm in the first few months. So this is the surface elevation traced with time. This is in metres. And this is the extreme event. So it's going from about -5 or so to about 18. Trough to crest. So it's about 25.6 metres, I think, is the deduced height of the wave. 2/3 of the Tom building high. So that's the sort of problem that you have to design for. And of course, these waves, when they come through, I mean, you have a storm that lasts for 2-3 days, building up, you get the peak and then it drops off. But, it's relentless, just hammering the structure. Now, clearly, in a 40-metre water depth or 30-metre, the physics of this don't work, but you still get very big waves. And that's what engineers need to contend with. Now, I'm going to talk very briefly about the suction caisson foundations, only because when I did my PhD, this was something that I was very interested in. In fact, my whole PhD was on it. But at the end of the PhD, so I came across, and the focus was for oil and gas problems. But towards the end, about 1998, we started to get interested in offshore wind. It was just starting. So I think we're probably one of the earliest research groups to be involved in this area. And in my PhD, at least in one of the chapters, there was a focus on how do you apply this sort of technology for wind turbines? And it's been a constant thread of work over the last 20 odd years, which we've been involved in. Now, why are they called suction caissons? Well, it's all about the way they're installed. They're essentially a large upturned bucket, steel cylinder with a top. And what you do is you lower them to the sea floor, and there's water inside and water outside. And then when they make contact with the sea floor, you let them sink into the sea floor a little bit. So there's a nice seal. And then you pump the water out of the caisson, of the internal cavity. That creates a downward force and pushes it into the ground. It's quite ingenious, really. It's a bit more complicated than that, but that's the basic principle. And here is an example. You don't even need it to be full of water. You can pump out air. As long as you can create the pressure differential, you can drive it into the ground. Now, you need to understand the resistances of the soil and all that sort of stuff, and there are calculations you can do. In fact, myself and my colleague Guy Hulsby have produced a set of calculations that is now used standard in the industry for this design problem. But here is a photo of caisson above ground, caisson installed. Takes about 2 hours. You just need a pump. So this is very promising for things like offshore wind because you don't need expensive construction equipment, which I'll talk about a little bit more in a second. It's also noiseless. So if there's a problem about noise, and some of the installation techniques create lots of noise, then this is useful. We have carried out huge amounts of work on this over the years. And the basic thrust of work is laboratory model tests using kit that we've designed and built. Field scale trials. So here are some experiments that we did in 2004. These are obviously not full scale. They're a quarter scale. So even when you do large tests like this, the caisson here is 3 meters in diameter. So it's still quite a big structure, and it's all designed by us. It's still only small scale compared to the real problem. Lots of work using computers, analysis theory, etc. develop theories, create design methods. That's the sort of structure of work that we do in the group. And actually now translated into design guidelines that we've written for the Carbon Trust recently with some consultants and one of the sort of contractors that fabricate these sorts of systems. But this kind of encapsulates 20 years of research at Oxford, as well as 20 years of knowledge in the industry of how you design these sorts of foundations and structures so that when you have to install 200 of them, it goes right. And they're starting to be used, but as I say, they're not yet taking off. And one of the problems is that if you have to build this sort of structure, you need to fabricate these jacket structures. And so there's a question of the supply chain. Where do you get them built? Can the supply chain deliver on time? You need 200. You need 200 by next June. Can they build them? Can they get the steel? How much will that cost? So there's big questions there, and that's one of the challenges. So we are more interested at the moment in piled foundations. And of most interest is the monopile foundation. And the main reason really is that it's a steel tube. It's a very simple construction. The supply chain is established. It's well used in the sector. People know about it. Maybe a couple of thousand have already been installed. Here is one up the top. You can just see there a person. There you go. It's a 6 metre diameter steel tube, about 30 metres, 40 metres long. So it's a pretty big piece of steel. Maybe weighs, I don't know, 600 tonnes, 700 tonnes. So it's also a very expensive piece of steel. And I guess one of the questions is, can you make it cheaper? Have they used too much steel? You might think it's a very simple problem, and I'll talk a bit more about that in a second. But, you know, in a way you've got diameter. That's all right. You've got diameter, you've got length, and you've got wall thickness. Only 3 variables to designing this steel tube. But as I'll explain, it's a bit more complex than that. They're installed by hammering them into the ground with a big hammer. Now this is a very robust process. You can install tubes, steel tubes, into most materials apart from solid rock. But most of the materials around the UK you can install these steel tubes into. If you have problems, you just get a bigger hammer. Or an even bigger one. The only problem is it's quite expensive. Obviously, to mobilise this bit of kit is quite expensive. You need to be able to handle big bits of steel. You've got to be able to handle the hammer. We're talking hundreds of thousands of pounds a day to mobilise this bit of kit. So, you know, a lot of cost in the construction. So we're going to talk about that because this is where the sector is. They like the steel tubes. The supply chain is there. The designers understand them. The certifiers understand them. So I'm just going to talk about how you might design them because that's what we've been into. Here is a monopile. And all we're going to talk about is, can we design the monopile to take a sort of horizontal force? And all we're interested in is, how much force can it take and at what displacement? How far does it have to go to take that force? That's the first question to answer. So I'm interested in the horizontal force, and I'm going to show some plots of horizontal force against displacement. Now, if you're interested in dynamics, you'd be interested in stiffness. So you'd be interested in what's happening here. What we're really interested in, or we're interested in that, but what we're really interested in is making sure when the force is applied, it doesn't fall over. So what you might be really interested in is making sure that you know where this point is. Because if it falls over, that's a real problem. Now, some variables, L over D is length divided by diameter. For monopiles tends to be 2 to 6. And the height of loading tends to be normalised by the diameter 5 to 15. A typical offshore oil and gas pile is about 2 metres in diameter and about 120 metres long, or 100 metres long, or maybe 80 metres long. They are very different to these sorts of piles. So it is new knowledge that's needed. Ooh. One of the other problems is that it's an industrialised design problem. We must design, so we have a site. There are many turbines on the site. We must decide L, D and T for each turbine. At each bit of the site, this is a profile of soil strength. Don't need to worry about the detail here. But you can imagine the soil strength at each part of the site with depth is different. So you have to produce a design process that can optimise the design across the site for all turbines that takes account of the individual site conditions for each turbine. So that's quite a complex problem. There's upwards of maybe 1 million calculations that are done by these companies in designing these turbines, trying to understand all the load calculations, trying to understand the different combinations of the foundation design, varying the location of each turbine. So they will do a site-wide optimization of the wind farm to vary the location of each turbine and the foundation design, and knowing about the wind field to optimize the power output of the farm. So this is a major optimization problem. Now what we need to do as engineers, and certainly as the geotechnical engineers, is feed into that process and make sure that they can calculate L, D and T properly. So, I'm just going to specify the problem a little easier, or a little more. Here is our wind turbine. We have to create a computer model, and this is probably about as much engineering as you really need to know, that we go from some schematic to a computer model, and we represent the interaction of the structure with the ground with springs. In fact, they're nonlinear springs, and there are codified expressions for these nonlinear springs, which are called PY springs. So if you see the word PY, that you'll see that is standard calculation. And there are codified methods. These codified methods have been in place for 50 years or more, and are for the oil and gas sector. The problem is that they're completely useless for the wind turbine problem, as I will show very shortly. And what happened is that when they started measuring their wind turbines and looking at things like natural frequencies and then comparing them to the design calculations, they were finding they didn't match. Now that had a big impact, because it impacts the fatigue life of the structure. And what they hope, obviously they need the structure to be there for 25 years for the business model. And if the fatigue life is impeded, then there's a problem. So this was recognised as an issue, and a major consortium of people put together to produce an answer. And the answer was this project called the PISA project, which was a 3-year project, cost £3.5 million, which we ran as the university in collaboration with many people. So the question they had was, can you produce better springs for us, preferably a simple analytical calculation? We said, yes, we can probably produce better springs for you, but not with a simple analytical calculation, because that's very hard. So we produced a project called the PISA project. It had 4 elements. It ran for 3 years. As I say, it cost £3.5 million. A lot of that money was in medium-scale field tests to prove the design methods. It's built around computational methods, in this case 3-dimensional finite element calculations, which we used to design some field tests to make sure that we understood exactly what was going to happen when we did the field tests. The idea was that the field tests would then validate the computational calculations. So these would be site-specific for the field test site. So we'd say, we've done a lot of work on this. We predict in advance this is what the results will be, and then the results show that our predictions are correct. If that is the case, we can then use this approach to develop simplified models that capture the appropriate physics in the problem. We can then use this. Of course, you can't do full-scale trials, but you can do full-scale calculations for wind farms using computational methods. So we can use this to calibrate our simplified models to specific wind farm sites. And then if you go through a number of processes, what you can do is develop parameterized calculations in which you can then specify the calculation to a particular site and allow it to vary for different sites. At the end of it, what you then can produce is a very quick calculation that is like this. You can do these calculations very quickly if you have a simple model with springs, but a 3D finite element calculation takes days. So you can't do that for all your wind farm designs. So you need these simple calculations. Then you can produce this simple calculation that hopefully is accurate, reflects the conditions. Now this is some output. This is horizontal load against displacement, as I talked about before. The red line is a specific finite element calculation. And the green line is the output from our new model to show, and just showing how close an agreement it is with the finite element calculation. And the way you set up these calculations, you do a parametric study. So you choose some outliers in your space of variables you want to understand. You do your finite element calculations for those, and then you can interpolate in the space for your design. And that's what we've done here. And just for your information, that blue line is the calculation you would carry out using the current design methods for that problem. And what you find is, firstly, there's an implicit factor of safety of about 2 in the calculation that people are standardly doing. And the stiffness is well out by a factor of about 10, actually, in this case. And that is why, when they were measuring their natural frequencies, they were out, because the calculation was wrong. We had a big team on this. I was the principal investigator for the academic team. It was structured as an industry-run project, so all of the money came from the industry. It was funded through the Carbon Trust. They have a special scheme for offshore wind in which partners put money into, and then they fund R&D. So these are all the partners. They are all the major wind farm developers in the UK. We had some other partners coming in. Ørsted were the lead partner, so they were the main contractor. They underwrote the work. We had a team of about 10 academic staff members, 2 postdocs, 5 PhD students working on this pretty much full time. We had an independent review panel that looked at all of our output, including people from design certifiers. And then we had people to do the work. So consultants and contractors to do some of the serious work. This is the timetable. We actually put the tender in for the work in about April 2013. We were awarded the contract and started in 2013, August. What was very important is that we had to produce our design methods ahead of doing any testing. So they said, we want you to put your money where your mouth is, produce the design methods, and then we'll fund the field testing. And now that's quite a challenge. So we produced our design methods in August. We then commenced the field testing, finished the work in 2016. In 2016, the work was already being implemented in wind farm designs, which are now being built and will be implemented in designs about to be designed. So here is some pictures of some of the work, of the testing really. The sites were chosen to reflect North Sea sites for wind farms. So they are specially chosen onshore, but reflective of offshore conditions. If you do this sort of work offshore, multiply the cost by about 10 to 20. Just not going to happen. So you can see piles that are embedded in the ground. These are 2 metre diameter piles that we tested. We did a number of tests on 760 millimetre diameter piles. We had lots of instrumentation, and we applied our loads at height using sophisticated hydraulic control actuators. This is the first instance of fibre optic strain gauges being used on driven piles. And they all work perfectly. It was fantastic. It means we've had fantastic measurements of strain in our experiments. And now fibre optics are being specified for wind farm deployment on piles and wind farm structures. This is a picture of the 2 metre diameter pile test. You can see this is a major piece of engineering. Yeah, I mean, the big bits of kit, costs a lot of money. The other interesting thing about this is we had to design the tests. And you have to design these tests for failure. Now, as an engineer, normally you're designing things not to fail. Normally we use a good factor of safety and all that sort of stuff. But in these experiments, we had to design things to fail. So that's actually quite tricky. Because again, you have to put your money where your mouth is. Now this is the output. It's just fantastic output. The black line, this is a horizontal load. You can see 2 meganewtons is the big loads, 200 tonnes. Displacement on this axis. Black line is the experiment as measured. The blue line is our prediction of the experiment. I mean, it's just, in geotechnical engineering, this is a fantastic result. Normally we use factors of safety of 3 to 5. This is the PY method, the traditional calculation estimate. If I'd used that for the design of the testing, none of it would have worked because I would have under-specified the loading systems and so on. Now, you can apply these sorts of calculations to some design conditions. This is an application of the method, just as a demonstration of what the savings might be. And actually, obviously, the savings depend on the soil conditions and various other aspects of the calculation. But the saving in the steel for some of the sites is between 30 to 40%. So this is a major, major saving when you multiply it across 100, 200, 500 turbines. This is horizontal load displacement. That is our calculation for a pile with a length to diameter ratio of 4. If you'd used the traditional method, that would have been the calculation. If you changed the design using the traditional method, you would have had to have increased the pile length by another 2.2 diameters to get the same ultimate capacity. So there's major savings to be had here if you use more sophisticated methods. The work has been recognised obviously by the industry. We put it in for an award at the ICE last year through the British Geotechnical Association, and it won first prize. Now, what was interesting about this is that it wasn't a research award. We put it in to a competition against contractors and consultants for an industry award. And it's the first time that this award has been given to a university-led consortium, which I was very happy with because I think that says a lot about the impact and application of the work. We got £1,000, which we donated to Red R, which we thought was a good thing. Lots of initiatives coming out of it. No time to talk about all of these. But, it's kind of, these things just balloon. We do a lot of work on monitoring of offshore wind turbine structures with different wind companies to try and demonstrate the outputs that we've got, how they match to reality. We have commercialised the calculation method through a company called Plaxis that designed geotechnical software. They produced a piece of software called Modito, which stands for Monopile Design Tool, which they're selling probably from next month. It's about to come out. We look at scour problems. Some wind farms have scour pits around the piles that are about 10 to 15 metres deep. That's a big scour pit. It's a big problem. So the question is the structure still stable when you take away that much of the ground? We've looked at layered material, and we currently have a project where we're doing field testing looking at piles in chalk, because a lot of the UK coastline sits on chalk. I'm now going to talk a bit about the next step, which is to do with cyclic loading. I've talked about monotonic loading, and we've kind of cracked that. I think we kind of know if you apply a constant load, a load to the pile or the turbine, we understand that. But of course, the loads being applied are cyclic. So the question is, how does that impact on design? Does the soil response, does the structure fatigue in any way? Can we predict it over 25 years? Can we be confident? So, we might be interested in this as the monotonic loading, but if you unload and then reload, you might get this sort of response. So you get hysteresis, which could be important. Does the stiffness change as you cycle? Does the response stiffen up or soften? There's some work actually completed by me and my colleagues, which show that the response stiffens with time, which changes the natural frequency. And do you get the thing ratcheting? If you apply enough force and sort of repeated force, does it gradually lean over? We don't want all our wind farms leaning over. Or not in my lifetime. So I've got a few videos here. I'm going to run just a fraction over. I hope that's okay. So you can see there's some repeated loading happening up here. Now, these tests ran for 2 days, and it's just cycling away to very highly controlled loads at about a frequency of 0.1 hertz. So here's the bigger test. This is speeded up, obviously, before you start. But this is a fantastic experiment, really, because there are 8 hydraulic actuators acting in concert to apply up to 4 meganewtons of load in this test. 2 very specific load levels. Now, it's really amazing. So here's the other test. So the thing is, here's horizontal load, here's displacement. What you get from these sorts of experiments is at small loads, you get very repeatable behaviour. You get these small hysteresis loops. On this plot is about 10,000 cycles, and they're just repeating over each other. So at some load levels, you get this very repeatable behaviour, and we want to be able to predict that. At other load levels, this is now quite high levels of loading, what you find is that the thing's gradually ratcheting over. And what we want to do is make sure that we get this behaviour and not this behaviour. We actually have done a lot of work on this, and we have some models that we have developed. On the left is an experiment, and on the right is our prediction of that experiment. And you can see that it's pretty good. Now, not obviously going to go into detail of this, but the aim is to see whether these sorts of models, which take actually as input the PISA type method that I described, can then be applied to design. It's a bit more trickier than that, because actually, in some experiments, if you apply the loads at very fast rates, you get a different response. So here is a pile test where the load was applied slowly, and here is a pile test where the load was applied very fast. And you can see there's a doubling in the capacity. So of course, if you get this impulse load, then actually you may have some reserves of capacity. So again, can we account for that in design? So this is the focus of the next 5-year project. How can we capture these cyclic effects in a rational design calculation that developers can use? So we've cracked the monotonic loading problem, cut costs there. Can we now move to cutting more cost by rationally including cyclic loading? And it's a major project, 5 years, lots of different work packages at Oxford, modelling, so finite element type modelling, lots of laboratory testing. There will be a major program of field testing next year and the year after. Lots of work on theoretical models, and then how does it fit into design? And again, as part of this process, before we do the field testing, we have to produce our predictions. Again, this is quite a challenging exercise. And when you watch the first test, and you know that there's a lot of pressure, I can assure you. There's a big team. I'm leading the work, but all of my colleagues are contributing in different elements. So it's a big academic activity. We've recruited some postdoctoral students. We've also recruited some PhD students. So we're training people through the different activities. And there's a big input from Ørsted in terms of their personnel on this project to make sure it's a success. They are very interested in making sure that this work is appropriate to the sorts of designs that they need to pursue in the future. What's the impact? Well, the PISA project, broadly speaking, for current design, maybe 300k per turbine, maybe more. For next generation design, certainly more. But actually savings in using smaller vessels and perhaps quicker construction time. Very hard to calculate those savings. If you can crack the cyclic loading problem, more savings to be had. Maybe 10% more, maybe more. But actually, when you go to the 15 megawatt turbines, it's the cyclic loading problem that is of most concern for the design. So if we wanted to move to these big turbines where there's really good economies of scale, this is the problem we need to solve. Obviously, the aim is to solve it in the next 3 to 4 years. Now, this is having an impact. So you could imagine this impact is for, say, Ørsted or a developer. But of course, these impacts are wider than that. Ørsted have bid in for next sort of the next set of developments of wind farms, as have other developers. And you see the impact of this sort of research in the prices that they have bid in for. And so this was last year, 2017 offshore wind auction price, 57.50, Ørsted's Hornsea 2 wind farm. Hornsea 2 happens to be near one of the PISA field test sites. So the Hornsea 2 sort of geology is very similar to the PISA geology. But, so 57.50 compared to 120 in 2015, a halving of the price. It is incredible, really. And part of that is coming from these sorts of design methods, such as from PISA, but also other work. Part of it's also coming from the increased confidence that designers, consultants, certifiers, banks have in the design process, in the calculations being used. And so actually the cost of financing is being impacted on this as well. So it's not just about savings from direct engineering, it's savings also derived because there's better confidence in the engineering. So that's the end. These are my concluding remarks. Civil and geotechnical engineering actually making really quite substantial contributions in this space, using rather sophisticated techniques to try and better design foundations for these wind farms. And actually, there are some big savings that are being made because of the uptake of these techniques. These techniques, as I say, are being used for next generation wind farm design. They're now slowly being fed into the design standards. So the calculations that are, say, 50 years old are now being revised. In fact, in the last week, I've been having input into how we might revise them to reflect these new types of calculations. And Oxford Engineering is really at the forefront. We are considered as the world leaders in this area of work. So I think I'll finish there. I have one more video. There are flashing lights on this video, so if you, they say on the news all the time, beware of flashing lights for the. But this is a time lapse of one of the sites, just to show you what happened. It's quite amazing. You know, these guys were on site for 3 months doing this work, and then 3 months at the other site. Yeah, you can't predict the weather in England. One of the sites was in a place called Cowden, which is just near Hull, and Hornsey is just off the coast near there. The other site was in Dunkirk, near, obviously in France, because that's representative of the North Sea sands, whereas the Cowden site is representative of North Sea glacial clay materials.
Do you test it destructively, or does it? I'm waiting for it to fall down.
No, the thing when you're testing these things, I mean, these are big bits of steel. You can't have them falling over.
I did wonder why you.
Yeah. You need to be quite careful. I mean, one of the really tricky things is we designed the steel so that we could measure, or design the wall thickness so we could measure strain. So you want to be able to measure a decent amount of strain with the measurement systems. But of course you don't quite know what the maximum force will be, although we can estimate it. So we want to be close to yield, but not at yield. And in one of the tests, we were very, very close to yield. In fact, one of the tests of the big piles where we had 4.5 meganewtons force on there, we were very close to yielding the steel. But that's about as close to failure as we come, in the sense of that.
Is the steel essentially standard steel?
It's standard steel. In this project, actually, because we were working with one of the steel suppliers, we could specify the grade of steel that we might want. And in fact, we got billets of the steel to test the yield strength. Turned out, however, although we could do that, and we did do that, when they delivered some of the piles, they used the wrong grade of steel, which is why I was very worried about the loads we were at for some of the tests, that we were very close to yielding.
Is corrosion relevant, or?
For these tests, obviously not,
Yeah.
but offshore, it's a very serious factor, and there's a lot of debate about the corrosion, how you might design for corrosion, particularly for the inside of the monopiles, which tend to be sealed, and so I believe that's quite a corrosive environment. The thing about the corrosion problem and fatigue is, like the design calculations I've talked about, 50 years old, those are also 50 years old.
Right.
And you know, there's a lot of discussion about those should be updated, because if they're updated, you know, it may be better fatigue calculations, you know, more fatigue life.
Why is the suction technique still promising?
The suction, I think the thing about the suction installed foundation is that firstly, the jacket structure seems to be a more appropriate design for the water depths that they're looking at now, which are 30 metres, 35, plus the turbines that you have on. Some developers did go for the suction caisson foundation and even had investment decision to go for it, but then had to change tack because of the supply chain, that the suppliers couldn't get the jacket structures in place in time. One of the problems is around the fact that you want to make the jacket light, or the structure light, so you need to take tension on the foundation. The ability of these caissons to take tension, they can take big tensions, because in fact it's limited by cavitation of the fluid. And if you have a big area and you've got cavitation, you can get big force. But it takes a big displacement to mobilise that force. And so there's a question about the displacement response and the stiffness response. And that's really the question. So what will happen is that they have installed probably about 30 of these structures now. Many of them are instrumented. They will then look at those measurements over the next couple of years, and that will then influence whether they go forward or not. But at the moment, they're not cheaper than a steel tube. That is basically how these decisions are made. What is the price of that? What is the price of that? That's cheaper. That's what we're going for. But all of the consultants and developers, they will run teams that are designing all of these different options. They just look at the bottom line. That's what we're going for.
Do you collaborate with the blade designers? Because presumably that as the design of the blades change, the forces which are coming.
Yeah, the fluids group do lots of work on blade design. My colleagues here. We don't tend to do. I think we're more interested in what are the forces, and then how do we input into that calculation to accommodate those forces. The thing about this design problem, it's so multifaceted that you need to spend 25 years to be on top of all the different facets of it. So focus on one thing, get that right.
As you look at the huge increase of demand for wind farm capacity and the potential for a transformational change in supply chains over the next 10 and 20 years, do you think that's going to change the way people think about design and the benefits of standardization versus the very specific design? For example, you have turbine by turbine across a wind farm.
So
if you said, if I make a standard design, I can pump this out at half the price.
What they find is that the problem is the variability of conditions across a site is very large. We're talking sites. These turbines are maybe a kilometre apart. You maybe have 200 of them, so you've got a big site. Some of the sites, I did some work many years ago on a site up in Scotland, and the variability of strength across the site was a factor of 20. And the variability of the soil stiffness was a factor of 100. So, if you go down that path, I mean, there are things that, I might just stop this because this might be getting a bit boring. For jacket structures, they do try to standardise. And they may have an element of the structure which is non-standard, but the rest of it is standardised. For the monopiles, they just basically, they can have that much more variable because all you're varying is the length. So they would standardise on the diameter and then think about the length. The wall thickness tends to be different all the way down the pile, by the way. So it's a bit harder than just LD and T. It's actually LD and many Ts. And in fact, the next step is, can we actually optimise the wall thickness all the way down? Because you can cut out maybe 50, 100 tonnes just by being more sophisticated in that area. So I think our aim is to move more towards an industrialised design process. The fabricators, obviously, where they can industrialise it, obviously they have to, but there will still be some element that has to be slightly bespoke, because that's where the competitive advantage of one developer over another comes in.
Just a question about the ease of work, sorry, that's all right.
Yeah.
So the scale of your test piles, you might say it's closer to oil and gas than wind turbines. So two questions on that.
Scale in diameter, but not length.
Sorry,
Yeah.
Do you think PY goes with poor assumption at any scale? And the second one, what do you think the validity of your tests at 10-metre monopile might end up with in a few years' time?
So I think the PY curve, in fact, our method includes the PY curves, just recalibrated. But we include other parts of the problem, which are not so necessary for very long piles. So, for example, you could imagine if you have a 10-metre diameter pile, the base shear, the shear at the base of the pile, is a very substantial number. Makes a big difference. So that's included in our calculation, which historically it was never included, because if you have a 100-metre long pile, the base shear doesn't actually come into it. The pile will probably form a plastic hinge somewhere up the pile. And the experiments are to prove that the numerical calculations, which are themselves scalable. So the problem is you're never going to be able to carry out to failure a test on a 10-metre diameter pile. Oh yeah, I have asked, but it's very expensive. Yeah.
If designers have used models which are inaccurate, as you suggest,
Yep.
presumably there are some wind turbines out there that have poor dynamic behaviour.
Yes.
Is there anything you can do once the thing is installed to tune that out?
Well, they can add in dampers and other systems to try and tune the system a bit better. They can add in mass.
I think there's some new techniques going on too, using remote sensors, LiDARs on the turbines. They can measure the wind before it strikes the turbine, so the blades can be feathered to reduce the fatigue loads. But that's still not quite out there yet. In the future.
Yeah, I mean the key thing is that they're probably not going to fall over. So because the calculations I think on the whole are more conservative than they need to be. So they've got more steel in them, but they are stiffer, and that people do have to do calculations so far as the dynamics are concerned, and they are repeating those calculations. Any other questions? Well, one more.
One of the back and one of the front.
Yeah.
I've been watching Western speakers making the blades. I used to have a small wooden honeycomb and then moved on to carbon fibre now. So is one of the answers to do a monopile using a much lighter material?
I think the problem is you have to drive it into the ground. The driving forces are quite considerable, and I think these sorts of other materials perhaps not as robust. Just as example, although we're talking about soil that these materials are going into, these piles are going into, it's not the sort of soil that you just see out on the football oval. It's really quite strong material. The glacial materials off the North Sea have very high strengths, have boulders included in them, quite considerable boulders. They were exposed to significant glacial action. So they are very strong materials. So you need a very robust system to get into them.
Is anyone installing them on ice or permafrost? Has that been explored yet?
I don't know about that, to be honest. I mean, I don't know.
Does anybody want to talk about any other locations?
I will be coming for a drink because I'm a bit thirsty now. So
There'll be plenty of them in Australia.
yeah.
Because University of Western Australia is a leading civil engineering university.
Yes.
So how much of the energy in Australia is dependent on renewables these days?
Not much, I think. Although, interestingly, where I grew up in Australia, this is a complete side story, which is a very remote town in Western Australia, 700 kilometres from Perth. It had the first experimental wind farm in Australia, probably in the Southern Hemisphere, I think, in 1984, supplying 20% of the town's electricity, has been continuously since. Esperance in Western Australia. They've replaced the turbines once, and they now have 2 wind farms, supplies 30%. The town has a diesel-powered power station, so it cuts that quite considerably. But generally, although there are some serious problems in Australia about energy, which led to the coup, the coup of the Prime Minister being cut. Most of it is oil and gas.
Okay, well, I think you'll all agree that it's been a fantastic lecture. I'm going to ask Professor Paul Buckley, the Secretary of the Oxford Energy and Alumni Society, to come and propose a vote of thanks. Paul?
Wow, Byron, you've blown us away.
Literally. good pun.
I should just say, it's such a pleasure to see you presenting this talk. I've known you since mid-1990s when you arrived as a fresh-faced graduate student in my college in Bailey when I was a tutor there. And it's been so marvellous to see you rise through the ranks and now have this, especially your appointment to this prestigious chair. You've done fantastically well. And the work that you've just been describing, I think to me, incredible thing about it is the scale of what you're dealing with, and both the products that you're designing for, and consequently the scale of the testing that you have to do to validate what you're doing, and consequently from that, I can imagine, although you didn't really talk about it, the costs, the numbers of thousands of pounds that you're having to justify in order to do the work. It really is an area where, as you put it, you're putting your money where your mouth is, in a sense that is not often true to quite such an extent in engineering.
Mm.
So it's fantastic work. You've explained it very clearly to us. The idea of tubes, steel tubes in bending. I guess since we're all undergraduates here,
We should know.
get that. But I know very well from what you and your colleagues do that there's an awful lot going on in the background there, particularly to do with soil mechanics, that actually makes it a darn sight harder than it does seem at first sight. But you've explained it so clearly to us, we've got this illusion that we actually have a good understanding of it. We've got this new length measure now, Morgan Tower. Very good.
Yes.
Which one?
So, as I say, we're left with this wonderful feeling we actually understand how we're going to generate. Is it 50% of the UK's energy
Well, I
by
don't know.
2030, according to your
Yeah, maybe.
numbers?
Who knows? Yeah.
So, fantastic. Really enjoyed the lecture, and let's put our hands together and thank Simon.